Hey, what's up everybody? Welcome to Stoichiometry and Solutions Part 3. Today is all about percent yield. So percent yield starts off with theoretical yield. So theoretical yield is the maximum amount of product that can be formed when the limiting reactant is fully consumed. And as always, it helps to think of an analogy. And the analogy I want to use here is imagine you are the owner of a factory. You manage a factory. And in your factory, you produce guitars. A standard guitar has 6 strings. So let's say in your latest shipment, you got 600 strings. You got 600 strings, and each guitar needs 6 strings. So hypothetically, you could make 100 guitars. The theoretical yield of what you have of your 600 strings is 100 guitars. But as we know, life isn't perfect and not everything is going to go the way you expect. Let's say in the process of making the guitars, some of the strings snap, and let's say some of them were faulty, some of them were just bad. Who knows what happened? But let's say at the end you only had 94 guitars. So at the end you ended up with 94 guitars. So although 100 guitars was your theoretical yield, yield, your actual yield is the 94 guitars. I don't know how to spell actual yield. As far as these numbers go, they're not that far off. If you made 94 guitars from 100 guitars, you were pretty efficient. Like you were 94% efficient. And that figure, that 94%, is exactly what a percent yield is. So a percent yield is just the percent ratio of actual yield to theoretical yield. And there's this kind of a formula down here where percent yield is actual yield over theoretical yield times 100%. So our actual yield of our guitar analogy was 94 guitars. But our theoretical yield from the 600 strings that we were given is 100 guitars. So you multiply that by 100%, and your percent yield comes out to 94%. Not bad. The same thing applies to chemical reactions. A lot of the time when you're in a lab and you're doing experiments, you're not going to have all your reactants turning into products. Something might go wrong. There's a lot of factors that play into what your percent yield is going to be. Now, ideally, you want to maximize your percent yield in any situation, but a lot of the times it's going to be basically impossible to get 100%, and it is going to be impossible to get over 100%. So if I give you those 600 strings, and I ask you to make 200 guitars, that's impossible. So your percent yield can never be over 100%. From a lab perspective, you always want to maximize your percent yield. Even if you're not going to get 100%, get as close to it as you possibly can. Okay, let's do a practice problem with this percent yield idea. And let's look at the 2015 National Exam question 2. So aspirin is prepared by the acetylation of salicylic acid according to the following equation. If the yield of this reaction is 83%, what mass of salicylic acid would be required to prepare 1.0 kilograms of aspirin? Before we really get started with the problem, let's understand what's happening. So we're told that some salicylic acid is being converted into aspirin, specifically 1 kilogram of aspirin. The important thing to realize here is that this transfer is only 83% efficient. And we're told that by the percent yield of the reaction here. What this means here is that we need to keep in mind that although we're producing 1 kilogram of aspirin, if the percent yield was 100%, we would be producing more aspirin. So if we want to relate aspirin to salicylic acid, we need to first assume what happens if this transfer was 100% efficient. How much aspirin would be produced if this was 100% efficient? And then use that to relate it to everything to do with the salicylic acid. So let's do that. So we know that 1,000 grams of aspirin is going to be 83%. So if we set up this proportion here and solve for x is going to represent how much aspirin would be produced if this reaction was 100% efficient. Okay, so X comes out to 1205 grams of aspirin. Okay, but it's not really helpful to work in grams. We're going to need to convert this value into moles. So we have 1205 grams of aspirin, and we need to find out what the molar mass of aspirin is. And so aspirin has a chemical formula of C9HAO4, which has a molar mass of 83 grams. Aspirin per 1 mole of aspirin. So really we have 6.69 moles of aspirin. Okay, the question asks us for the mass of salicylic acid. But currently we have aspirin. So how do we relate moles of aspirin to moles of salicylic acid? Well, aspirin and salicylic acid are in a 1-to-1 ratio. What that means is that if we have 6.69 moles of aspirin being produced, then that means 6.69 moles of salicylic acid, I'm just going to say SA, was consumed in order for all of this aspirin to be produced. So all that there's left to do is find the mass of 6.69 moles of salicylic acid. And in order to do that, we need to multiply by the molar mass of salicylic acid. And since salicylic acid has a chemical formula of this, it has a molar mass of 138 grams. And so this all comes out to about 924 grams of salicylic acid. But the real answer, if you're doing this on the test, the answer choice that you would go with is 0.92 kilograms of salicylic acid. And that is your answer. The big thing to realize here is that even though you're preparing 1 kilogram of aspirin, this 1 kilogram is being produced under 83% yield. So you need to first convert 1 kilogram to what that value would be if you had 100% yield. And then use that to relate it to salicylic acid, and then find the moles of salicylic acid and then convert that into mass. All right, that's it for percent yield. I hope you were able to learn something, and I hope to see you later. Thank you.